Structured Query Language, or SQL, is a powerful tool for interacting with databases. This presentation explores how SQL is being used in big data technologies, bridging the gap between traditional databases and modern data systems. Here are the reasons why SQL is used in big data. First, SQL is a standardized query language that data professionals understand, so it is easy to use. Second, it acts as a bridge between traditional databases and modern big data systems. Third, it enables analytics without learning specialized frameworks, saving time and effort. Fourth, it democratizes data access across organizations. The evolution of SQL in big data can be traced through several key phases. In the 1970s, we saw the rise of traditional SQL with relational databases that emphasized ACID properties, which stands for atomicity, consistency, isolation, and durability. The 2000s brought Hadoop and MapReduce, which allowed us to handle larger datasets. During the 2010s, SQL began to be used on Hadoop, leading to the emergence of Hive, Impala, and Presto. Since 2015, modern SQL engines like Spark SQL and Flink SQL have offered improved performance. Today, we're seeing the rise of cloud-native SQL, where serverless SQL engines operate at scale. Here are some key structured query language technologies in big data. First, Apache Hive, which is a SQL-like interface built on Hadoop for data warehousing. Second, Spark SQL, which is a SQL engine integrated with Apache Spark's processing framework. Third, Apache Impala, which is a massively parallel processing SQL engine for Hadoop. Fourth, Presto or Trino, which is a distributed SQL query engine optimized for analytics. Fifth, Apache Drill, which is a schema-free SQL query engine for Hadoop and NoSQL. Finally, Cloud SQL engines, which are managed serverless SQL query services. Apache Hive is a data warehouse system built on top of Hadoop for providing data query and analysis. Here are the key features of Hive. First, it has a SQL-like query language called HiveQL. Second, it provides tables with schema on read. Third, it uses a metastore for schema management. Fourth, it supports multiple storage formats. Fifth, it supports user-defined functions, or UDFs, and custom serializers. Hive can be used for data warehousing, batch-oriented processing, and log analysis. Here is a sample HiveQL code. Create a table with partitioning, then load data into partition. On the architecture side, Hive has 3 layers. The first layer is the HiveQL interface or driver. The second layer is the query compiler, optimizer, and execution. The third layer is Hadoop, HDFS, or MapReduce. Spark SQL is a component of Apache Spark that allows you to process structured data using structured query language. Here are some of the key advantages of using Spark SQL. First, it has in-memory processing for faster queries. Second, it uses a Unified Application Programming Interface, or API, with data frame and data set. Third, it uses Catalyst Optimizer for query optimization. Fourth, it integrates with Spark's machine learning library. Fifth, it supports structured streaming. This is an example of SQL syntax in Spark where we select the category, average revenue as average revenue, and count distinct customer ID as customer count from sales, where the transaction date is greater than 2023-0101, grouped by category, having the count greater than 100, ordered by average revenue descending. This is an example of the data frame API using Scala code. On the architecture side, Spark SQL has 4 layers. The first layer is the Spark SQL interface. The second layer is the data frame or dataset API. The third layer is the Catalyst Optimizer. The fourth layer is the Spark Core or RDD. Let's explore SQL performance optimization techniques for big data. The first technique is table partitioning. Segment data by specific columns. Improve query performance by pruning partitions. This is commonly used with time-based or regional data. In the example code shown, a table is created partitioned by year, month, and day. The second technique is columnar storage. Store data by column instead of row. Columnar storage has better compression ratios. Only read columns needed for the query. It is suitable for Parquet and ORC file formats. In the example code shown, a sales data is created in Parquet file format. The third technique is query optimization. Use column pruning and predicate pushdown. Filter early in the query execution. Optimize joins with appropriate strategy. Use appropriate aggregation methods. In the example code, there are steps to join the users table. The fourth technique is caching and materialization. Cache frequently accessed data in memory. Create materialized views for complex aggregations. Pre-compute results for common queries and consider data refresh strategy. In the example code, it shows the creation of materialized view with date, product ID, and sum of amount. A modern data processing pipeline with structured query language typically involves several stages. The first stage is data ingestion, where data is loaded from multiple sources. The second stage is data storage, where structured data is stored in optimized formats. The third stage is data processing, where extract, transform, load, or ETL processes and data transformations occur. The fourth stage is data analytics, which involves dashboards and advanced analytics. The fifth stage is data consumption, which includes data-driven applications and self-service platforms. SQL plays a role in several of these stages, including schema definition, transformation, and analytics. There are several structured query language best practices for big data. The first practice is to optimize your joins. Always join tables with the smallest result sets first, as join order matters significantly. Consider using broadcast joins for small tables and bucket joins for large tables. The example code shows a more efficient join with smaller dataset first. The second practice is to use partitioning wisely. Choose partition keys that align with your most common query patterns. Avoid over-partitioning, which can lead to small file problems. Date-based partitioning works well for time series data with a retention policy. The example code shows a query to select records from orders table using order date range. The third best practice is to use appropriate data types. Choose the smallest data type that can reliably store your data. This reduces storage requirements and improves query performance. Use int instead of bigint when the range is sufficient, and varchar with appropriate length limits. The example code shows a table definition with appropriate data types. The fourth best practice is to filter early and often. Apply filters as early as possible in your query execution to reduce the amount of data processed in later stages. Push predicates down to source tables before joining to reduce intermediate data size. The example code shows an efficient way to filter out the records using transaction date. Here are the future trends of structured query language in big data. First, cloud-native SQL engines. With the rise of serverless structured query language query engines optimized for cloud data lakes. These services provide on-demand scaling with separation of storage and compute for cost efficiency and performance. Second, real-time SQL processing, with streaming structured query language engines that enable continuous queries over real-time data streams. This allows for immediate analytics and real-time decision making with familiar structured query language syntax. Third, artificial intelligence and structured query language integration, with integration of artificial intelligence and machine learning capabilities directly into structured query language engines. This enables in-database machine learning and prediction functions using standard structured query language, democratizing access to advanced analytics. Fourth, structured query language on multi-model data, with structured query language engines that can query across various data models, relational, document, graph with a unified interface. This enables more flexible data architectures while maintaining structured query languages' declarative simplicity. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.